We are happy to have Dr. Yevgeny Stadnik from University of Sydney telling us about searching for ultralight scalar dark matter with muonium and muonic atoms. So please begin.
So thank you very much for the introduction, and also thank you very much to the organizers of the seminar series for inviting me to present today's talk. So the topic of my talk essentially is about how we can search for ultralight scalar dark matter. I'll review some of the slightly older results in the field, and then I'll also discuss a more recent idea in terms of how we can search for ultralight scalar dark matter by using muon-based atomic systems. So the motivation for trying to understand the identity and microscopic properties of the dark matter comes essentially from a number of independent astrophysical observations, which collectively tell us that there is about 5 times more dark matter in the universe than the ordinary baryonic and luminous matter that we see around us. And what we understand from the astrophysical observations is that a substantial fraction of this observed dark matter is confined to the galaxies where it forms these spheroidal dark matter halos. And from the point of view of direct detection experiments, there are 2 important features of the dark matter to take into consideration. So first of all, in the local vicinity of the solar system, we know that the average energy density of the dark matter is estimated to be about half a proton rest mass per cubic centimeter. And we understand that this is an extremely small density compared with the ordinary matter-based densities that we're familiar with in the terrestrial environment. But also this is quite a small energy density compared with even some of the best vacuum systems that we can prepare in the laboratory ourselves. And the smallness of this density is in fact one of the reasons why it's extremely challenging to devise a successful experiment to actually detect and identify dark matter in a purely laboratory setting. The other important feature of the dark matter is that in the local vicinity, we infer or estimate that the average speed of the dark matter, or root mean square speed, should be of the order of 300 kilometers a second. And this number basically ensures that the dark matter neither escapes from the gravitational well of the galaxy, and nor does the dark matter collapse into the center of the galaxy, at least over a cosmologically large timescale. So 300 kilometers a second is about 1,000th of the speed of light. And so what this implies is that the galactic dark matter is a relatively highly non-relativistic form of matter. And in fact, the non-relativistic nature of the galactic dark matter turns out to have important consequences for how we try to devise experiments to see dark matter in the laboratory. So over the past several decades, the majority of experimental efforts in terms of searching for dark matter directly have tended to focus on so-called weakly interactive massive particles, or WIMPs for short, and their canonical mass range lies somewhere from about the rest mass of a proton up to about 10 times the Higgs boson mass. So this is a relatively familiar range of particle mass scales, at least from the point of view of the standard model of particle physics. However, in light of the continued absence of strong experimental evidence for these types of particles, there's slowly been some growing interest over the past decade or 2 in terms of searching for alternative dark matter candidates. And one of the interesting possibilities, which has started to attract significant attention over the past decade or so, is that the dark matter may potentially consist of bosonic particles with extremely small masses that live in the green region over here. And what we see is that the complementarity of these 2 mass ranges, in fact, will necessitate the use of conceptually very different types of approaches to look for the different types of dark matter candidates. And I'll explain some of these key differences very shortly. So the simplest type of bosonic particle that we can have is a spinless particle, and the field in this case could be described by a real field. In other words, there would be a single degree of freedom in this case. So this is the simplest possibility if we want to consider particles with the minimal number of degrees of freedom. And if these low mass spinless particles were produced in the early universe, then they can subsequently form a coherently oscillating classical field phi. So the field in this case would be essentially characterized by two parameters. So one of the parameters here involves the angular frequency of the oscillations, and this is governed or set approximately by the rest mass energy of the dark matter particle. And the second parameter here involves the amplitude of the oscillations, phi 0. And we see that these oscillations would take place about the minimum of this harmonic or quadratic potential over here. So as a result of the oscillations of this dark matter field, there's going to be a certain energy density stored in the oscillations. And the time average energy density in this case is going to be a function in terms of the frequency of the oscillations as well as the amplitude of the oscillations. And dependence of the energy density on these two parameters is precisely what we would expect for the usual underdamped harmonic oscillator. Now, the way that we can get these oscillations essentially comes from the observation that the dynamics of a spinless field in expanding universe is analogous to the dynamics of a system which is described by a time-dependent differential equation, which essentially mimics a damped harmonic oscillator with this time-dependent frictional term in blue here. So the parameter h is what provides the frictional term, and h is the Hubble parameter, which basically parameterizes the relative rate of expansion of the universe. So at least in the earlier times of the universe, the Hubble parameter scales inversely proportionally with the age of the universe. So in other words, the Hubble parameter was at its largest at some point in the very earliest times of the universe. So at these very early times, the Hubble parameter can be much larger than the scalar particle mass. In this case, we have essentially the overdamped regime. And so the scalar field in this case would basically remain stuck somewhere up in this harmonic potential. And so the scalar field value on these very short time scales, at these earliest times, would not appreciably change over time. As the universe continues to expand, the relative rate of expansion decreases, and so eventually we could encounter a situation when the Hubble parameter now becomes comparable to the scalar particle mass. And so at this time, we enter into the critically damped regime. So the scalar field in this case can now start to essentially slowly roll down into the potential here. And in this case, the scalar field value can now start to appreciably change away from its initial value. And as the universe continues to expand even further, the Hubble parameter continues to decrease, and eventually it can be much smaller than the scalar particle mass. And so now we enter into the underdamped regime, where the scalar field is basically free to oscillate about the minimum of this potential here. Now, as the universe continues to expand and the Hubble parameter continues to decrease, then in this case, what we see is that not only do we have oscillations, but the amplitude of the oscillation will start to become damped over time. And the damping is in such a way that the energy density stored in the oscillations will redshift with the scale factor essentially inversely to the third power. In other words, the energy density scales inversely proportionally to the volume of the universe, which is the same relation that we have for non-relativistic matter or dust-like particles. So what we've just described here is colloquially referred to in the literature as the vacuum misalignment mechanism. It's a non-thermal production mechanism in its simplest incarnation, in the sense that the final abundance of energy or final dark matter abundance that we produce is not governed by microscopic interactions, but rather is determined by the initial conditions, namely by how high up the scalar field initially sits in the potential here. So the higher up that the scalar field initially sits, the more dark matter we will tend to produce at later times. So as I mentioned already, the energy density in this case will scale inversely proportionally to the volume of the universe. And also, quite importantly, the time averaged pressure associated with the field will be much less than the time averaged energy density. In other words, the oscillations of this field will basically mimic a cold, pressureless fluid in this case. So in other words, we have all of the main ingredients to have essentially what is quite a good cold dark matter candidate in this case. Now, the reason why the oscillations of the dark matter field are expected to be coherent is that the galactic dark matter particles are understood to be cold or non-relativistic. So this means that the kinetic energies of these dark matter particles are all much smaller than the rest mass energy of the dark matter particle. And so the overall energies of the individual particles are all going to be very similar, and the total energies are going to be given approximately by the rest mass energy of the dark matter particle. And this is important because it's the energies of the particles which determine the angular frequency of the oscillation in this case. The oscillations will not be perfectly coherent, however. In a local galactic region where the local root mean square speed is estimated to be about 300 kilometers a second, we expect it to be a finite characteristic spread in the kinetic energies at the level of about 1 part per million relative to the rest mass energy of the dark matter particle. So we can equivalently state this as saying that there should be a finite coherence time associated with the oscillations of this dark matter field. And the coherence time in this case will be of the order of 1 million periods of oscillation, which basically means that the oscillations of this dark matter field are going to be nearly monochromatic. And the quality factor which is associated with these nearly monochromatic oscillations is going to be of the order of 1 million, which is actually quite a high quality factor, even compared with some of the better resonators and cavities that we have in the laboratory, for example. So just to explain this notion of temporal coherence in terms of some illustrations, down the bottom left here, we see that if we perform measurements on a time scale which is much less than a coherence time, then looking at the zoomed in inset at the top left here, we see that on these 4 time scales, the amplitude of the oscillation of this field will remain approximately constant over time. However, if we continue to perform measurements on a time scale which becomes comparable to the coherence time or greater than the coherence time, then now we would expect the amplitude of the oscillation to fluctuate over time in some sort of stochastic manner. And the fluctuations of the amplitude in this case would be expected to be governed by some underlying probability distribution function. So in the simplest case, where we consider the standard Halo model, where the individual particle velocities of the dark matter essentially take on a quasi-maximum Boltzmann type distribution. In this case, we'd expect the fluctuations in the amplitude of the oscillation of this field to follow essentially the same type of distribution function as the Rayleigh type distribution shown in the red curve here. And this is essentially analogous to the Rayleigh type distribution that we also see, for example, with a chaotic or thermal light source in conventional physics.
Excuse me?
Oh, yes.
This classical field phi, do you assume that it is independent of x, I mean, the position, or is there any reason why it becomes, I don't know, position independent? I don't know.
So generally speaking, it's not position independent. So when I've written this expression here, I do neglect the motional gradient term. So the full expression has energy times time minus the dot product of the momentum and the position vectors. But what we can usually do is, because the dark matter particles are highly non-relativistic, the typical contribution of the momentum-dependent term or the position-dependent term it tends to evolve at a rate which is about 1 million times slower than the contribution of this mass energy term, which is a temporally varying function. So here I basically just press these much smaller spatial gradients when I write down this expression here, but they are in fact there.
Okay, so the result does not change too much, even if you allow for x dependence.
That's right. Yes.
Okay.
Sorry. So in that case, so in the left plot, so I think we need some non-linearity to obtain this kind of evolution, right? So what kind of equation did you actually solve?
Well, I mean, in principle, we don't necessarily need non-linearity. In this case, these amplitude fluctuations arise. Okay, so there's the bare mass energy term, and there's the spatial components. Now, if we ignore those components, we also have to consider the random kinetic energy contributions from all the individual particles. So essentially, what happens is if we look at this expression for the oscillating scalar field, this is basically summed over the individual wave functions of all of the numerous particles. So when we sum all of the individual wave functions at any given time and position, we have a particular overall amplitude, and there's also a certain overall phase. I also haven't written the phase, but there is generally a phase here. Now, what happens is, over time, the random kinetic energy contributions, which I've neglected to write here, will tend to give a sort of random, ever-changing overall phase and amplitude in this expression here. We can only strictly write down this sort of coherent form if we're performing measurements on a very short time scale, which is much less than the coherent time in this case. But to answer your question, we don't necessarily need non-linearities in this case to get this to get these fluctuations.
I see. So in this plot, so this is like an effective zero mode by taking into account non-zero modes. So
yes, that's right. Because there are finite contributions from the fact that the individual particle velocities are not zero. If the particle velocities were all zero, then what we would see is just what we see in the zoomed-in inset. It would just be a constant fixed amplitude and phase over time, and so nothing would would change in this case. Yeah.
Yes, thank you.
Okay, so this is the issue of temporal coherence. Spatial coherence works in a similar way, but as I mentioned, the spatial gradients tend to have a smaller effect here. Okay, now the question is, how do we get a classical field? In order to have a classical field, we need to have a large number of these low mass dark matter particles contained within a single de Broglie volume. And for the local galactic dark matter density, we can satisfy this classicality requirement, provided that the dark matter particle mass is less than about 1 electron volt or so. So in other words, we're talking about extremely light particles, which are at least 1 million times lighter than the electron in this case. For these particular types of low mass dark matter fields, we are particularly interested in the particle mass range from about 10 to minus 21 electron volts up to about 1 electron volt or so. So this upper mass cutoff of 1 electron volt is simply just from the requirement of classicality here, just like above. However, what I'll mention is that if this dark matter field was not necessarily classical or bosonic, then the dark matter particle mass could in principle be much larger than electron volts. On the other hand, if these low mass dark matter fields make up any substantial fraction of the observed dark matter, then the particle mass cannot be arbitrarily light. And the reason for this is that with these low mass dark matter fields, we expect it to be a suppression in the formation of structures on the level scale below about the de Broglie wavelength of the dark matter field. And this is basically a consequence of the wave uncertainty principle. And so the main observation is that as the dark matter particle mass is reduced, the de Broglie wavelength tends to grow. And for a sufficiently low mass dark matter particle, we get a de Broglie wavelength which is astronomical in size, and eventually it would become too big, and we would run into contradictions with, for example, the structures that we see in astrophysical measurements of the London forest. So this gives a low mass bound of about 10 to minus 21 electron volts. There's an even simpler argument from the point of view of requiring the dark matter de Broglie wavelength to fit inside the halo sizes of the smallest dwarf galaxies that we see around us. And this very simple argument gives us a very similar low mass figure of merit of about 10 to minus 21 electron volts as well. So basically we have this very broad range of possible dark matter particle masses, which spans about 20 orders of magnitude. And what this implies is that we can have a similarly broad range of possible frequencies of oscillation. So these frequencies here can range anywhere from about 100 nanohertz, where the period of oscillation is conveniently of the order of a month. And we can go all the way up to about 100 terahertz, which corresponds to the infrared region of the electromagnetic spectrum. So even though we have this very broad range of possible frequencies, the fact that these frequencies are physically understandable from the point of view of many everyday physical phenomena means that we can actually try to devise experiments which cover a very sizable region or subregions of this possible frequency space. Now, the interesting question is how exactly we can go about searching for the effects of these low mass dark matter fields. In traditional WIMP dark matter searches, we normally look for particle-like signatures. So for example, if there's a stream of WIMP dark matter particles, then they can potentially interact with, for example, the nuclei in an array of atoms, for example, in the liquid state or with a solid state detector. And these interactions between the WIMP dark matter particles and atomic nuclei can induce, for example, a nuclear recoil by depositing energy onto the nucleus. Now we can see a particle-like signature. With these low mass dark matter fields, searching for particle-like signatures is practically impossible. The reason here is that these low mass dark matter fields are made up of particles which are not only very low mass, but the particles are also highly non-relativistic. So the maximum kinetic energies carried by these dark matter particles are going to be at most of the order of micro electron volts, and this is many orders of magnitude below the energy threshold in these traditional WIMP dark matter detectors, where the energy threshold is typically of the order of a kilo electron volts. Now, what we can do, however, is actually turn what may seem like a disadvantage around and actually discover a new opportunity, which is that with these low mass dark matter fields, we have a situation where there are numerous low mass dark matter particles contained within a single de Broglie volume, which means that all of these low mass dark matter particles can act together coherently or in unison. And in this case, what can happen is that all of these dark matter particles acting together can exhibit field-like behavior in the form of, for example, wave-like signatures. Now, the exact types of wave-like signatures we can produce will, of course, depend on the type of dark matter candidate that we have, and also the signatures will depend on the types of non-gravitational interactions that these dark matter fields may have with ordinary matter. So if we keep restricting ourselves only to the possibility of spinless dark matter candidates, there are still basically two broad possibilities in terms of the types of couplings that we can have. And these are distinguished according to the parity of the underlying field. On the one hand, we can have scalar types of interactions, which are even with respect to the parity operation, that is under the inversion of all the spatial coordinates. Or we can also have a pseudoscalar type of interaction, like an axion-like particle interaction, where the underlying parity is odd. And what is interesting is that this simple difference in the sign here can give a very big difference as far as the experimental signatures are concerned. So scalar dark matter, on the one hand, can induce apparent spatial temporal variations of the so-called fundamental constants of nature, whereas pseudoscalar dark matter can induce a number of time-varying spin-dependent effects. And without going into too many technical details, what we see from the example down the bottom of blue here is that the optimal way in which we can search for these different types of signatures is going to be different in the two cases, and we have to use different types of experimental techniques and platforms. Now, in the interest of time, today I'd like to focus only on the left hand of this page, which is how scalar dark matter, first of all, can induce apparent spatial temporal variations of the fundamental constants. I'll briefly, also recapitulate. The types of some of the types of techniques which have been suggested to look for these types of signatures, and then I'll also discuss a newer development in terms of how we can use muon-based atomic systems to also look for these types of variations of the fundamental constants. Now, before I discuss the effects of ultralight scalar dark matter specifically, I'd briefly like to recapitulate some of the more traditional ways in which these ultralight scalar particles have traditionally been probed and studied phenomenologically. Perhaps the most obvious signature of an ultralight scalar is if we have the coupling of this scalar field phi to some nanomolar fermion, then this will lead to the exchange of a scalar boson between two fermions in vacuum. And this type of single particle exchange induces the usual Yukawa type potential between these two particles, between the two fermions. And so in the presence of this potential, we expect it to be an extra force generated between these two fermions. So these are basically additional fifth forces. What is interesting about these fifth forces is because the interaction here only involves the coupling of the scalar field to some particular mass energy component of an atom. This could be, for example, the electron mass or the nuclear masses. The point is that these interactions don't couple to the overall or universal mass energy component of an actual test body in its entirety. So what this basically means is that if we look at test bodies made up of different materials, for example, different elements or different isotopes, there are going to be different relative contributions from the electronic mass components as opposed to the nuclear mass components. So what we can have is that different test bodies can in principle fall at slightly different rates in the vicinity of another source body in this case. And this will constitute a violation of the weak equivalence principle in this case. Another interesting avenue for studying the effects of feebly interacting scalars, as well as pseudoscalars, is in the form of astrophysical phenomena. So, for example, if we have the interaction of the scalar field phi with the electromagnetic field tensor in the standard model, then it's possible to produce these scalars from the interiors of very hot astrophysical bodies, such as stars. So here, for example, we have a Primakov type conversion of a hot photon into a scalar, and the second photon leg in the coupling is provided by the electric field of one of the charged ionic particles in this hot plasma. So generally speaking, the rate of emission will tend to increase if we have stronger interactions. And the consequence of this is that with any source of emission of these scalars, what we're basically doing is we're having an additional energy loss channel, or another way of putting it, we have an additional local energy sink. And in the presence of a local energy sink, what will tend to happen in the case of an active star such as the sun, which is actively burning fuel in order to maintain hydrostatic equilibrium, that is to counterbalance the role of gravity. In this case, what will tend to happen is the star will tend to contract, and this will tend to increase the temperature so as to give us a higher rate of burning of nuclear fuel in order to counteract the greater gravitational pressure in this case. On the other hand, if we look at a dead star like a white dwarf, for example, then in that case, the additional emission of scalars from the interior of the white dwarf would actually constitute an increased cooling rate in this case, because a dead star no longer has to burn any nuclear fuel in that particular case. Regardless of the specific mechanisms, the important point here is that if the emission or energy loss processes are sufficiently strong, then we can run into a contradiction between, for example, astrophysical measurements relating to, for example, stellar evolution, as compared with expectations from standard model predictions for how stars evolve. So in principle, astrophysics provides us with a very powerful handle for probing a variety of bosonic particles in this way. A third and much more recent possibility in this context of ultralight scalars is what can happen, at least experimentally, if these low mass scalars make up at least some fraction of the galactic dark matter halo which we live in. And here there are a number of interesting new possibilities which have emerged over the past decade or so. And one of the interesting features about ultralight scalar dark matter is that it may induce apparent variations of the fundamental constants of nature. One of the simplest ways in which this can occur is if we have the linear interaction with oscillating scalar field phi with the electromagnetic field tensor F from the standard model. So this type of coupling would induce apparent oscillations in the value of the electromagnetic fine structure constant alpha. This is just a constant which parameterizes the strength of the electromagnetic interactions in the standard model. And so the oscillations in alpha here will take place at a frequency which is governed by the mass of the dark matter particle. And the size of the oscillations in alpha are going to depend on the amplitude of this oscillating dark matter field. And also the size of the oscillations in alpha will be inversely proportional to the new physics energy scale lambda, which appears in the denominator of our interaction in this case. There is in principle, of course, another similar coupling involving the coupling of the scalar field to the standard model fermions. In this case, we'd expect it to be apparent oscillations in the values of the fermion masses, and the new physics energy scale in the second example would in principle be need not be the same as the new physics energy scale above. And even further, we can say that in principle, the two scales need not necessarily be related to one another. They can potentially be decoupled to some extent. Another interesting observation when we consider laboratory experiments is that the laboratory and the solar system are orbiting about the galactic center in much the same way that the stars in our galaxy also are known to orbit about the galactic center. However, the dark matter halo itself is understood to be more or less at rest in the galactic frame of reference. So what this means is that we expect to be some relative motion between the apparatus and this background dark matter field. And so in this case, what this means is that if we perform measurements in a laboratory frame of reference, then the expression for the oscillating scalar field phi here will also be supplemented by this additional motional gradient term in red here. So this is in some ways similar to, for example, the expression for a standing wave. Now, if we have the linear phi interactions here and coupled together with this motional gradient term in red, then we will expect it to be forces exerted on test bodies and test masses in a laboratory in this case. And these forces should be directed along the motion of the test particle through the background dark matter halo. Also, these forces should be oscillating in time because of the oscillating nature of the dark matter field. And as I mentioned on the previous slide, or a couple of slides ago, because the interactions here are coupling not to the overall mass energy content of an atom, but rather only some specific mass energy contributions, such as the electronic mass contribution or the Coulomb binding energy, the forces induced on test bodies in this case will be expected to violate the weak equivalence principle in this case. So this, at least experimentally, is a nice feature because it allows us a very convenient handle to disentangle these forces from the usual gravitational force, which we know respects the weak equivalence principle. Apart from linear and phi interactions, it's also possible to have analogous quadratic and phi interactions. So these phi squared interactions could in principle arise in a model which has some underlying Z2 symmetry. A Z2 symmetry would basically preclude odd powers of the scalar fields from appearing in the interactions which we can write down. And with these sparse-code interactions, we have, of course, the same types of Wasserian time signatures as we do in the case of the linear phi interaction above. However, with sparse-code interactions, it turns out that we actually have a much richer phenomenology because of some extra effects. And just to briefly mention two of these effects. First of all, with a sparse-code interaction, we have an interesting situation where we can have slow changes in the values of the fundamental constants, which are correlated with changes in the dark matter density locally. And this can happen most simply, for example, if we consider the expansion of the universe, because we know that at the earliest times of the universe, for example, when the light primordial elements were first being produced, this was up to about 3 minutes after the birth of the universe. In this case, the dark matter density was much larger than what it is today in a local galactic halo. So here we expect to see a change or difference in the values of the fundamental constant correlated with this big difference in the dark matter density in this case. Another interesting effect, which can occur if we have a phi-squared coupling, is if we consider measurements in a laboratory environment where we're close to a massive body. So we understand that Earth or the Sun should, to some degree, induce deformations or gradients in the dark matter density around them. And so what we expect to see in this case is that in the vicinity of a massive body like Earth, we would expect it to be additional equivalence principle violating forces which are directed along these dark matter density gradients when we have these phi-squared interactions. So that's some of the basic theory. Now, in terms of experiments, there's been a growing body of work now performed to search for the effects of these ultralight scalar dark matter fields using a number of new ideas. And most of these searches have tended to focus on the electromagnetic and electron couplings of the light scalar fields. And the reason for this is that these two couplings essentially induce oscillations of alpha and the electron mass, which are two parameters, two fundamental constants which are ubiquitous in natural phenomena. For example, if we look at the energy level structure of an atom, the energy level spacings in a non-relativistic limit and neglecting magnetic interactions simply fail proportionally to the Rydberg constant. So we see that there's, of course, the defined structure constant alpha and the electron mass in this case. Or if we look at, for example, a solid material, we know that the length of the solid scales proportionally to the atomic Bohr radius in a non-relativistic limit. So this means that, again, we see the defined structure constant alpha and the electron mass appearing here. And the point is that if alpha or the electron mass were to vary, then this in principle gives us a very convenient handle for searching for these types of scalar photon scalar electron couplings. For example, we can compare different types of atomic transition frequencies. We can compare different types of optical cavities, and also we can compare atoms to cavities. We can also build much more complicated experiments. For example, large-scale gravitational wave detectors, which are based on the principle of laser interferometry. They have a number of optical components. And here we see that the lengths or thicknesses of these components will change if there's an oscillation in alpha or the electron mass in this case. And for example, if the thickness of the central beam splitter here were to change over time, we would expect to see a small phase shift developing between the two arms in this case. In other words, there'll be a small optical path length difference, which will temporarily manifest between the two arms in this case. Atom interferometers are another possibility which have been proposed. Basically, we can have two spatially separated atom interferometers, which are essentially manipulated with a common laser beam. And the laser beam basically allows us to excite atoms from the ground state to the excited state and then de-excite to the ground state. So if there are going to be oscillations in alpha electron mass, this energy level separation between the two levels would change over time. And so as we continue to perform all of these laser manipulations, there's going to be a certain phase shift developing between, phase shift difference developing between these two spatially separated atom interferometers at the end of this interferometric sequence here. These are just some of the basic ideas which have been proposed. There's a recent overview which can be found, for example, in the SNOMAS process from last year, as well as numerous references inside. But the main, inside here. So just to illustrate some of the main results which have been obtained in this field over the past several years. So these are the limits which have been obtained for the linear interaction of this oscillating scalar dark matter field phi with electromagnetic field tensor, which is basically the photon coupling. So down the bottom left, we have limits from the clock comparison limits shown in blue. And also just to the right, we have the clock cavity comparison limits in red here. So the limits in blue and red both came about from searching for these oscillations in alpha due to this oscillating dark matter field. So on the x-axis, we have the logarithm of the dark matter particle mass. So larger dark matter particle masses go to the right in this case, and also higher frequencies of oscillation will also go to the right. On the y-axis, we have the logarithm of the new physics energy scale here, and feebler interactions in this case will go down the page. So basically, the limits in blue and red have collectively given us up to a factor of 10,000 improvement over the complementary laboratory searches in green and yellow. Now, the experiments in green and yellow do not specifically look for signatures of an ultralight scalar dark matter field. Instead, what these were are basically torsion pendulum experiments, which look for the equivalence principle of ionic force, which is mediated by the scalar particle between a source body and a pair of test bodies in the experiment. So these are complementary signatures in this case. If we go to the higher dark matter particle masses, we also have limits from optical interferometry experiments, the best of which come from the G600 collaboration. This is basically a 600-meter detector in Germany, and it's selected the limits in light blue here. As I mentioned, the other main coupling which has been probed is the scalar coupling with the electron. The phenomenology there turns out to look very similar, so I won't show what the graph looks like specifically. But what I will mention is that for the scalar electron coupling, the bit force bounds in yellow and green turn out to be about a factor of 20 weaker, whereas the light blue region here stays where it is. So it turns out that the optical interferometry searches have more available parameter space to probe that particular case. So the scalar electron coupling is more phenomenologically friendly when it comes to the scalar, searching for the dark matter signatures. I'll also mention that the Planck scale limits to show where the green line is on the graph. So basically what this means is that for the entire range of scalar particle masses on this graph, the new physics energy scales which have already been ruled out all happen to lie above the Planck scale, which is another way of saying that the interactions which we are probing are intrinsically feebler than the gravitational interaction. Now, the picture starts to look different and qualitatively different if we look at the quadratic interaction of the scalar dark matter field to the electromagnetic field. So first of all, we see that the Planck scale, which we now show on the left-hand side in this case, with the Planck scale living here, what this means is that the new physics energy scales which we can have can in principle lie below the Planck scale in this case, which is different compared to the previous slide, even if we compare over the same mass range as before. The phenomenology also looks qualitatively quite different. So down in the bottom left here, we have the clock comparison limits shown in blue. So these come about from searching for these oscillations in alpha due to this oscillating dark matter field. If we go to the right here, we have the astrophysical Big Bang ecosynthesis bounds in red. And these are basically, these limits basically come about from searching for a slow change in the value of alpha as we go from the earliest moments of the universe when the light primordial elements were produced, and then going all the way to the present day when we have a much smaller dark matter density. So basically the limits in blue and red here have collectively given us up to a 15 orders magnitude improvement over the previous and complementary bounds which have been obtained in purple and gray. So the purple bounds here are laboratory bounds and gray bounds here are astrophysical bounds. And the purple and gray limits here again did not look specifically for the effects of dark matter as when we were comparing to the fifth boss limits in the previous graph, but rather they're looking for processes which involve either, for example, exchange of virtual particles or the production of scalar particles from a hot body in this case. So essentially, most of the interest in studying these ultralight scalar dark matter fields phenomenologically and experimentally has tended to focus on the electromagnetic and electron couplings. But what about the possibility of searching for the effects of these ultralight scalar dark matter fields through different types of couplings, for example, the scalar-muon coupling? In this case, we understand that in principle, there could be a flavor or generational dependence of these scalar coupling strengths if we consider the leptonic sector. Indeed, even if we look at the standard model, we know that the electron, muon, and tau masses are different because the three different flavors or generations of leptons couple with different strengths to the Higgs boson in the standard model. So in principle, it's possible to have a similar type of effect arising with an extrascalar field. There's potentially extra motivation for studying the couplings of hypothetical new particles to muons, which comes from the persistence of a number of quite long-standing anomalies now in muon physics, in fact, over the course of, I believe, more than a decade now. And two of these interesting puzzles are the so-called proton radius puzzle and the muon G-2 puzzle. Now, in principle, both of these puzzles may be able to be resolved using essentially conventional physics. But if they're not resolved with conventional physics, then in principle this opens the doorway for some interesting sort of muon-philic physics potentially. Another interesting feature about studying the phenomenology of the couplings of light bosons to muons is that unlike, for example, more ordinary stable particles like electrons, there are actually no known stable terrestrial sources of muons. And this can lead to a qualitatively quite a different phenomenology if we consider the scalar-muon coupling and compare it to the scalar-electron coupling. For example, a scalar-electron coupling is very strongly generally very strongly constrained by tests of the weak equivalence principle, whereas in the case of muons, we don't actually have any stable source of muons inside Earth. So in principle, equivalence principle violating force bounds can to a large extent be largely evaded in that case potentially. So as I mentioned, these oscillating dark matter fields may induce apparent oscillations in the values of the fundamental constants, such as the fine structure constant and the fermion masses. So one of the fermion masses is, of course, the muon mass. And one of the ways that we can probe these oscillations in the muon mass is with muonium spectroscopy. So muonium is a bound state of an electron and an antimuon. It's a relatively short-lived atom whose lifetime is basically determined by the finite lifetime of the muon itself. So that's about 2 microseconds. So this is essentially an exotic atom, which only lives a very short time. The reduced mass of the system is given approximately by the electron mass in this case, and there's also a small correction coming from the electron to muon mass ratio as well. So because this is a simple two-body system, the energy level structure of muonium turns out to be very similar to the energy level structure of hydrogen, which is exactly solvable. And so if we consider, for example, the simplest electronic structure in the non-relativistic limit, when we ignore the magnetic interactions between the two components, in this case, the energy level structure is described by the usual Rydberg formula. So we see that if we were to measure this 1s to 2s transition interval, then we're going to be sensitive to oscillations in alpha as well as the electron mass. This is because of the variation in the Rydberg constant. What is more important for us, however, is this small sensitivity to oscillations of the muon mass that we gain here because of the small role of the electron to muon mass ratio in determining the reduced mass of the system in this case. If we want to have a larger sensitivity coefficient, which is not suppressed according to this small ratio of masses, then we can start to consider energy level structure with account of the magnetic interactions of the two components. So if we allow for magnetic interactions, then in principle we can have a dipole-dipole type interaction where, depending on whether the two spins are aligned anti-parallel to one another or parallel to one another, we can have a slightly different energy for these two spin orientations. And with this type of magnetic hyperfine splitting, we have the perhaps slightly less well-known Fermi formula, which essentially tells us that because of the presence of the interaction of the because of the presence of the muon moment, the participation, of the muon magnetic moment in this interaction, we expect it to be 1 power of the muon mass appearing explicitly in the denominator in this case. So what this means is that this ground state hyperfine splitting interval is going to be significantly more sensitive to oscillations of the muon mass as compared with the 1s to 2s interval that we saw above. Now, there are, in fact, quite a large number of existing data sets which can allow us to probe these oscillations in the muon mass by using various spectroscopy measurements with muonium and also various muonic atoms. The currently best existing data sets that we have to do this actually come from a number of muonium spectroscopy experiments, which were done at Los Alamos in the US in the 1990s. And here, the two best data sets come from the 1s to 2s interval in muonium and the ground state hyperfine splitting interval in muonium, which is much more sensitive to oscillations in the muon mass. Here, the estimated sensitivities with existing data sets are shown by the red and blue lines, respectively. So what we expect to be able to do in this case is we can expect to improve the sensitivity over the astrophysical bounds by up to 7 orders of magnitude in this case. And the astrophysical bounds in this case primarily come from two different sources. So for scalar masses bigger than about 10 to minus 18 electron volts, the primary astrophysical bounds are from the consideration of supernova energy loss, supernova energy loss arguments. So basically, in the hot environment or medium of the supernova 1987A, we can have the emission of scalar particles from the muon content inside the proto-neutron star. Whereas if we go to the scalar particle masses less than about 10 to minus 18 electron volts, the primary sources of the primary source of astrophysical bounds actually comes from the possibility of the radiation of these ultralight scalar particles from a compact binary system which contains at least one neutron star. And these astrophysical bounds turn out to be much more stringent. So just to briefly explain where the nature of these bounds, we know that in a neutron star, there is in fact a stable abundance of muons because of the very high, typically very high Fermi energy of electrons in the neutron star. And because a neutron star is going about in a circular elliptical orbit in the compact binary system, it's an accelerating source of muon charges, which can allow us to emit scalar particles in the form of dipole radiation in this case. If we consider the quadratic interaction of the scalar dark matter field to the muon, then it turns out that the astrophysical bounds in that particular case turn out to be significantly weaker. And what this allows us to do is it opens up an even broader range of possible scalar particle masses, which we can efficiently probe with existing data sets from these two transitions in muonium. And here, in fact, the peak sensitivity which we can achieve is a little bit higher, is up to about 8 orders of magnitude compared with the astrophysical bounds in gray in this case. Now, what I've said so far is basically made the assumption that these scalar particles make up at least some fraction of the observed dark matter. We can still, in principle, probe the scalar-muon coupling, even if the scalar particles don't necessarily make up the dark matter. We simply look for different signatures in this case. For example, the scalar field couples to the electron field and the muon field, and we can have the exchange of a scalar particle between an electron and a muon. So this gives rise to the Fermita form of the Cauchy type potential in this case. And if the electron field in this case is sourced by the electronic content, for example, inside Earth, then if we perform local measurements, the measurements of the local acceleration due to gravity, that is little g, by using test bodies which contain muons, such as muonium, then we'll encounter a situation where we'll see a slightly different value of g as compared with an experiment which does not use any test masses containing muons. In other words, what we'd see is some apparent violation of the weak equivalence principle, depending on whether the test bodies used muons or did not use muons in this particular case. And there's some good news on this front because recently, about a year ago now, there was an experiment which was funded and now started at the Paul Scherrer Institute, known as LEMIN. And basically, this experiment aims to measure the local acceleration due to gravity using muonic test bodies with a relative precision of about 10%. And if we can achieve this relatively modest precision of about 10%, it should be possible to probe the combination of electron and muon coupling constants in this case down to the regions marked by the red curve in this case. And so if we achieve this 10% relative precision on the value of G, we expect up to a 5 orders magnitude improvement of the combined astrophysical and terrestrial bounds shown in light gray. And the improvement is even more if we compare with the existing bounds from muonic spectroscopy measurements, which essentially consider the intra-atomic exchange of a scalar particle and the effects on, for example, the 1s to 2s interval as measured in experiment versus what we get in terms of theory. So to summarize, in recent years, we've seen growing interest in terms of searching for ultralight scale dark matter fields, and the emphasis has overwhelmingly been on the electromagnetic and electron couplings, simply because the electromagnetic and electron couplings tend to have ubiquitous consequences for various physical and natural phenomena. However, we should, of course, not lose sight of the possibility of probing other types of couplings. For example, if we have a scalar-muon coupling, then it's possible to have apparent oscillations of the muon mass. And one of the powerful possible probes of this coupling would be muonic spectroscopy. So with existing datasets, I estimate that it should be possible to improve the sensitivity by up to 7 orders of magnitude for the linear coupling of the scalar field to the muon. And in the case of the quadratic coupling of the scalar field to the muon, I expect up to an 8 orders of magnitude improvement in sensitivity with existing datasets and over an even broader range of scalar dark matter particle masses in that case. Now, if the scalar particles don't necessarily make up any fraction of the observed dark matter, then it's possible to search for different types of signatures. So, for example, we can search for the scalar-mediated forces if the scalar field couples to the electron and muon fields. And in this case, with ongoing muonic free fall experiments, which measure the local acceleration due to gravity, we expect to be able to improve in terms of sensitivity to the combination of the electron and muon couplings by up to 5 orders of magnitude in this case. So on that note, I would like to conclude. I'd like to thank you very much for your attention, and I'm happy to answer any questions and discuss further.
Okay, thank you very much. Are there questions or comments?
Questions. I mean, it was not clear to me how the time dependence enter in the bounds of the muonic spectroscopy. You're talking about oscillation. I understand there's a formula, but now, what is the data that allows you to see this time variations?
Okay.
Data.
So,
you said with all the data you
yeah,
got.
So,
what is
yeah.
really the?
So I personally don't have the data, but I know roughly the sort of data that exists. So maybe just to explain, I guess, where the sort of different sensitivities sort of arise and the different sort of scaling. Generally speaking, if we consider these oscillating dark matter fields, the oscillation amplitude grows inversely proportionally to the mass of the dark matter particle. So at smaller dark matter particle masses, the scalar field amplitude becomes bigger, which means, generally speaking, a bigger effect. So as we move from the right to the left, the sensitivity tends to increase. The peak sensitivity of these data sets generally comes about when the period of oscillation of the dark matter field becomes comparable to the overall sort of duration of the data set. So if the data sets, in this case, the data sets are of the order of, say, 5 to 10 years each, the peak sensitivity will arise at a scalar mass, which is for where the period of oscillation is of the order of 5 to 10 years. So this is where we get the peak sensitivity. There are also some other important timescales in the data which are collected. So one of the very important timescales, apart from the duration of the data set, is how quickly we can acquire individual measurements of an individual transition frequency. So we can describe this by, for example, what is known as a cycle time. It tells us basically every cycle we collect one data point. These cycle times tend to be quite long. So for example, with the hyperfine structure measurements, I think this was of the order of 10,000 seconds. So this is about 3 hours. In the case of the 1s to 2s interval, I think it's more like it's actually several days. So when we actually start to go to frequencies of oscillation which are above these basically Nyquist frequencies, we see that the actual sensitivity to this coupling parameter starts to deteriorate faster than when we're sort of in the optimal range between the Nyquist frequency and the frequency set by the inverse of the duration of the data set. So that's the basic essence of where the sensitivity comes from. But of course, to actually get the limits, the data itself should be analyzed, but I don't have the raw data set to analyze myself. So these are just estimates for what can be done with existing data sets. So no one's actually done a dedicated search yet for this type of coupling with these data sets.
Maybe my question is also related with Alex's question. So are you really, so because you don't show any experimental data you are using, so are you do you use delta nu over nu, the uncertainty in the delta nu from the data, or
Yes.
So basically delta nu over nu, that's what you are using. You are not really observing the time dependence, right?
Yes. So to estimate these sensitivities, I use the published. So there are published data which tell us how precise the data set is when it's integrated over a certain amount of time. And basically the sensitivities are for the hyperfine structure splitting interval, the relative precision in the transition frequency is about 10 to the minus 8. And for the 1s to 2s interval, it's about 10 to the minus 9. So with these known sensitivities, at least over a certain time range, we can estimate what the sensitivities of the data sets are going to be to some oscillatory effect, because we know the duration of the data, and we know roughly how often it's samples, and we know the precision of the measurements when it's integrated over the total time.
And then in the delta nu, which uncertainty is more dominant? Is it systematic uncertainty or statistical uncertainty in the data?
That's a very good question. Yeah, that's a very good question. I don't actually remember. Yeah. I think what they want to do with new experiments is actually go to stronger muon beams to get better statistics. But these measurements may actually be currently limited by systematics. There's also another issue, which is also how to compare measured values with experimental, with theoretical values as well. And there, theoretical predictions technically are slightly more precise, at least for the hyperfine splitting interval, because one of the uncertainties which goes into, for example, predicting these intervals is also coming from sort of indirectly from experiments, because to also extract a very good prediction, we need to know, for example, independent quantities like I believe electron to proton mass ratios for these types of intervals as well in some cases. Yeah.
Thank you. And today you basically focused on the scalar particle, light scalar particle, but not pseudo-scalar particle, right? So, I mean,
Yes.
use completely different experimental data for pseudo-scalar case, I guess. And I mean, in general, all the constraints are at the similar level to the scalar case, or for the pseudo-scalar and the scalar case? Exclusion product, I mean, the range of excluded region is at a similar level?
So I haven't analyzed the pseudoscalar case, but the phenomenology for the pseudoscalar case is generally going to be quite different. So scalars, they give us this apparent oscillation in muon mass, whereas pseudoscalars, they will give sort of more like a spin precession effect. So in that case, we're not specifically looking for oscillations of the muon mass. And I think one of the big differences in phenomenology will be that for the scalar coupling, we're probing sort of a non-derivative interaction where the effect tends to grow as we decrease the scalar particle mass, because the scalar field amplitude grows as one on the scalar mass. Whereas for the pseudoscalar coupling, it's derivative in nature. So in that case, the sort of sensitivity will generally not tend to grow as you go to smaller masses, because there's an extra power of the particle of the boson particle mass, which we extract when we operate on the scalar field with a derivative operator. So if we look at the combination of the mass times the amplitude, that should be independent of the mass of the particle. So the landscape could look very different. Instead of lines which go down like this, we could see lines, I don't know, going horizontally instead. But I don't think anyone's actually done a dedicated analysis for muonium, looking for this type of coupling.
Thank you.
Yeah.
Thank you very much.
Yeah. But if you're interested in discussing, I mean, that's something which could be interesting to discuss and collaborate on if you're interested in. There are ways, I think, to do it. Yeah.
Maybe too naive a question, but is there any possibility to use mu plus, mu minus?
Mu plus, mu minus. So true muonium. So experimentally, I think it hasn't yet been observed.
Okay.
The experimental challenge with true muonium is that normally, so muonium has a relatively short lifetime, which is dictated basically by the finite lifetime of the muon. But in true muonium, if we replace the electron with muon, there's another decay channel which appears, which is that we can have the simple electromagnetic decay of the muon and antimuon. So the lifetime of true muonium is going to be expected to be much smaller than in sort of ordinary muonium. So in that case, it's much more short-lived, and also the states will be broader. So this actually been quite a challenge to try to see and synthesize muonium, but people are interested in trying to synthesize true muonium, and hopefully one day it should be possible. But nobody's managed to do it just yet from what I understand.
Okay, thank you. Are there further questions or comments? Okay, otherwise, we might thank Yevgeny again. Thank you very much.
Thank you very much.
Thank you very much for having me.
Thank you very much.